Okay, now we're going to see how perspective number 4, impulse and momentum, tie into simple harmonic motion. And I have to be honest with you. In short, we really don't do much when it comes to impulse and conservation of momentum when it comes to oscillating systems. It's not that you can't use it, it's just not particularly useful. Beyond that, in a course like this, in order to do anything meaningful, you would have to use calculus because a force versus time graph is a sine curve, and the only way to calculate the area under any portions of the curve would be to use calculus. So we're not going to use it. There is one notable exception that I can think of to using impulse and momentum to do simple harmonic motion, and that would be in deriving a formula for the period of a pendulum. So the moral of the story is, you can use this perspective to analyze the motion, it's just not real useful. And as a result, you don't see it show up in your textbook. I even checked some of my intermediate physics books, and I couldn't find anything on the momentum perspective, with the exception of using angular momentum to understand the oscillations of a pendulum. So beyond that, we're not going to be doing anything with it. Now, what I want to do is go into our first case study. And our first case study is going to be looking at a mass spring system, a horizontal mass spring system, and periodicity. And basically, periodicity is just, looking at the oscillation. How long does it take for the oscillation to occur? What's causing the oscillation? And so basically what we're going to be doing here now is a proof to come up with a formula for determining the period of a mass spring system. So I want to review something with you very quickly as it relates to frequency. And basically what we had was frequency is equal to 1 over the period. And we also have omega. Omega is defined as theta over t, or delta theta. But if theta initial is 0, then it just becomes theta over t. Now, if you go in a complete circle, then that means you're going to go 2 pi radians in one period, in one cycle. So it becomes 2 pi over t. But 1 over t is the same thing as frequency. And so we can write omega as 2 pi times the frequency. So we're going to see this, and I just want you to know where it comes from. So we get these two equations, f equals 1 over t, and omega is equal to 2 pi times the frequency. This is going to be really important in this proof. The case study basically is going to be taking multiple perspectives to fully analyze the phenomena of a mass spring system. What is physically going on there? So from kinematics, we had earlier said that V was equal to minus omega A sine omega t. And if you recall, at that time I said that the sine omega t, that this is basically a scaling factor, and it's going to take on values anywhere from 0 to 1. And omega A was the same thing as saying V max. Now, as a quick review, what that basically meant was this. We looked at a particle which was moving in a circle, and we basically used a bridge equation to say that V is equal to omega r. Now, when you flip that circle upwards so that it's eye level, because right now this is the top view, we're looking down on it. But when you look at this so that you're at eye level with it and you're looking at it from the side, then what you see is that back and forth motion. where the distance from the center of the circle out to the edge is what we would normally call the amplitude. And so what we're seeing is when the particle is located right here, we're seeing the entire maximum possible speed, which is constant on the overhead view, but it's not constant in the side view where you see it going from side to side, right? So you're going to see it oscillate from side to side. So we're going to write this as v is equal to omega a, and so that's where this v max comes from. V is equal to omega a. We're going to ignore the negative sign because it's not particularly useful at this time. And it's basically just for directional purposes, and we're not going to be needing that. All right, now we also earlier on from energy came up with an expression for omega, or I'm sorry, for Vmax, and we said that Vmax was equal to the square root of Ka squared over m. And so now what we want to do is we want to relate these two quantities. We want to take this velocity and that velocity and set them equal to each other so that we get omega a is equal to the square root of Ka squared over m. We can pull out the a squared and get omega a is equal to a times the square root of k over m. A's cancel, and what we get is omega is equal to the square root of k over m. So this is the angular frequency for an oscillating mass spring system. So this is where we have to utilize the 2 pi times the frequency for omega. So we're going to write 2 pi times the frequency is equal to the square root of k over m. So frequency is equal to 1 over 2 pi times the square root of k over m. And this equation here you should know. But this isn't the period, and we want to know what this is for the period. So the period is going to be the inverse of all of this. So if frequency is equal to 1 over the period, you could write 1 over t is equal to 1 over 2 pi times the square root of k over m. And basically, solving this for t, you just have to flip everything over, so you get t is equal to 2 pi times the square root of m over k. All right, now this is the equation that I wanted you to know. All right, it is not important that you understand how to derive this equation. Okay, I can't emphasize that enough. You don't have to know how to derive it, but you do have to understand what it means, what it's telling you. And what it's telling us is that the period is determined by the stiffness of the spring and how much inertia you have in the system. What the period does not depend on is the amplitude. And you might be asking yourself, well, why not the amplitude? Well, because with a larger amplitude comes larger forces. Larger forces means larger acceleration, and so ultimately you just cover more distance. Okay, before we go on to our second case study, I just want to point out one more thing, and that is that this equation that we have here for the period of a mass spring system, this is going to be valid for all mass spring systems. Okay, in other words, this is going to be both horizontal and vertical. In our next case study, we're going to take a look at the simple pendulum.